Anyway, rates of change. So yeah, dy dx f prime of x means the slope at a given point. And you could say that that is the rate of change in y with respect to x. That's actually what the d means. It's actually delta. So we're talking about changes in y against changes of x. So we have some made up word problems that make it seem like this stuff is very real world. I mean, it is, but it's not this low level of question. According to psychologists, the ability of a person to understand spatial concepts is given by capital A equals 1/3 square root t. So I'm assuming capital A stands for ability, where t is this person's age in years, and we're talking about people between the ages of 5 and 18. Okay. It says find the rate of improvement in ability to understand spatial concepts when the person is 9 and 16. The moment you see rate, your job is to think derivative. Okay? That is your job. Bless you. You're welcome. So what are we going to do for part A? We're going to find our derivative first. So what we have is capital A equals 1/3 t to the 1/2, because this will be much easier to find the derivative of, right? And our derivative will be a prime. So a prime is, drop that 1/2 down, multiply it to the 1/3, 1/6, and then subtract 1 from the 1/2 power, negative 1/2, which cleans up to, because this has a negative exponent, belongs in the bottom of the fraction, 1/6 root t. There. That is the function that will give us the rate of improvement in abilities. So when you want to tackle AI and AII, you just plug in 9 and 16 to this. A prime of 9 is, I forgot to change colors, so I guess we're doing this whole front in purple. 1/6 root 9, which is 1/6 times 3, 1/18. And double I, same trick, plug in 16, 1/6 root 16, 6 times 4, which is 1/24. So before we even move on to part B, let's talk about what this is showing us. The number 1/18 is considerably larger than the number 1/24. So what is that hinting at? Well, what it's hinting at is that the rate at which you can improve your ability to understand spatial concepts is slowing down. This rate is slowing down as we get closer to 18. This would imply that the younger the brain, the faster the rate of improvement is. You can't teach an old dog new tricks, kind of thing.
Yeah, we can.
Okay, so that's what this is talking about. Part B, I'll switch colors now. Part B says show that the derivative dA dt is always positive. Oh, well that's easy, because your first derivative only has one critical value on it. See, the first derivative will never equal 0. Its only critical value is when t equals 0. It would be undefined. That's because, you'd be talking about an infant that's fresh out of the womb. But we were specifically told between 5 and 18. So you have a sign diagram that has endpoints on it. 5, 18, without a single critical value in between them. So legitimately, you could just test any value you want between 5 and 18 and plug it in and show that it's positive. Look, you just did 2 of them. Or you could say that since the square root of t is always positive, 1/6 root t is always positive. So it really doesn't matter how you want to say that. The sign diagram proves it. I mean, you just found 2 values on it. There are no critical values. And like I said, square root of t is always going to be a positive value. So there you go. So what does it mean that the derivative is always positive? Not that the rate is increasing, because we saw here that the rate was decreasing. But the fact there's always improvement. That's what it is. It shows that a person has the ability to always increase. No, because if you're increasing the rate, you're implying that you are now picking up new skills faster than you used to. You see what I'm saying? So we have the ability to continue to learn during those years. That's what it always being positive is showing you. That because it says the ability to understand spatial concepts will go on and you will continue to have the ability is what it's saying. You got a question for me or no? Yeah. So that's what the always positive slope implies. Now, we did see here though that as time went on, even though it was positive, it was getting smaller. That implies that the rate at which we are learning is slowing down. That's the second derivative, you see? Oh, show that the second derivative is always negative and comment on the significance. Okay. Blue. Blue feels good. C. In order to find the second derivative, I am going to take the derivative of this function. So I don't have to mess with these radicals. So a double prime. I'm going to bring that negative 1/2 down to the front and multiply it to my 1/6. Negative 1 over 12. And subtract 1 from the negative 1/2, giving me negative 3/2. And just like we did here, we're going to put that on the bottom of a fraction as a radical. So I have negative 1 over 12, and we can say the square root of t cubed. Like that. So how do we show that it's always positive? Well, once again, first of all, your domain only goes from 5 to 18, and the square root of every number between 5 and 18 cubed is going to be positive, because 5 cubed is positive, 18 cubed is positive, everywhere between is positive, the square roots of all those will be positive, and overall you have a negative fraction. So what I did to show that it was true is I just did like this. This is a negative number, and this is a positive number. It's like there, it's always negative. But what is the significance of that? What is the significance of the fact that the second derivative is always negative? Even though you always have the ability to learn new skills between 5 and 18, the rate at which you master those skills or pick up those skills slows down. So it's going to take you longer and longer time to pick up new skills, but you can still pick up new skills. It's just going to happen at a slower rate. So that's what's up on that one. Now, if this was a IB exam question and they said explain or what does that mean? You guys had a question like that. The deer population question, you guys remember that one? When you were, and I think it was on the derivatives. It was a trig question, derivative of a trig question, and you were supposed to comment on the results of the fact that the derivative was negative there. And honestly, all you had to say was population's decreasing. Like, that's it. You don't want to say too much because you could talk yourself out of points really easily. Okay? So when you have a question that says, it wouldn't say comment, it would say interpret those results, keep it basic. If it's worth 1 mark, even if it's worth 2 marks, keep it basic. If it's worth 2 marks and you write 3 sentences, assume you're probably talking yourself out of points. Be very, very, I don't want to say vague. Let's say broad. Don't get too nitty gritty. Don't try to be fancy. Okay? Yeah. The fact that the first derivative is always positive implies that you always have the ability to learn new concepts. But the fact that the second derivative is negative implies that even though you have the ability to learn new concepts, the rate at which you pick up those skills is slower and slower and slower. It's kind of like you're going really fast in your car. You put your brakes on. So while your brakes are slowing you down, you're still going in the same direction you were traveling in. So there is a time at which you are still heading to the, let's just say, to the right, but the rate at which you're heading to the right is slowing down. Okay, you can think of it like that. Alrighty. Let's flip them over. Talking about cost. The cost in dollars of producing X items in a factory each day is given by this ugly polynomial. This is going to be a calculator question, so I'll save you the trouble of typing it. No, when I say calculator, I mean because you don't want to multiply by the decimals. I'll save you the trouble and tell you what the values are when you plug it in, okay? Because that polynomial is really bad. It says find C prime. And by the way, C prime is called the marginal cost function. Remember I told you guys that quote unquote passing the IB exam for this course, at least at the University of Florida, gets you credit for business calc? That's because they do this kind of math a lot in business calc. It's a big deal. They apply the derivative. So it's called the marginal cost. Anybody ever seen Shark Tank? You know, they always ask them, what are your margins? This is what they're talking about. The marginal cost is found using the first derivative. So we're, what? Oh God, hold on, let me pause the video. Anyway, back to reality. Okay. Yeah, it's recording again. We're good. As long as I don't hit the red button, we're in good shape. Let's find C prime. We got to bring down this 3 and triple the 13, so it gives us 3 zeros and a 39. 0.00039 x squared. We have to bring down this 2 to double this 2, so 2 zeros and a 4. And then plus 5. There, part A. The marginal cost function. Part B asks us to find the marginal cost when 150 items are produced. Well, this is the marginal cost function, and X is the number of items we're producing. You legitimately just plug in 150. So for part B, we're just trying to figure out what is C prime of 150. So you're going to put 150 there and square it. You're going to put 150 there and multiply it by 4. And then you're going to add 5. Can you all just trust me that it's about it's exactly 14.375? You would just plug in 150. But this is cost, right? This is money. So we're going to have to round this to 2 decimals. So the marginal cost is about 14.38. So what does this marginal cost do? Because it says to interpret the results. This function is telling you what the cost of producing an X number of items is. This function tells you the rate at which the cost is changing. Okay? So what this just told you was, when I've produced 150 items, the rate is increasing by about 14.38 for each additional item. Does that make sense? So what it's doing is it's giving you an estimate of making the 151st item as well. That's what you would be using it for, is to estimate the cost of making that next item, because it says it's growing by 14.38. That's the interpretation. It's currently, the cost to produce these items is currently going up by 14.38 each additional item when I've made 150 of them. I would like to point out that this is a parabola, a positive parabola. which means that it has a minimum. It does not have a maximum. Now, where is that minimum? It's, negative b over 2a, whatever that gives us. It gives us a negative number. Did you catch that, though? Negative this over double this is a negative number. The implication being, we are to the right of that minimum. This marginal cost is going to continue to go up for each item I produce, is what it's saying. And because it's a parabola, it's actually getting faster and faster and faster. I'm just telling all the things that are true because of derivatives. It's not part of the question. So now let's do part C. And part C is legitimately just to see, just to find out, let's do that. Part C is legitimately just to find out if our marginal cost function is doing a good job of estimating this cost increase. Part C says find what the cost of producing 151 items is, and then subtract the cost of producing 150. Oh, so we need to know those two values. So first of all, we'd have to plug in 151 to this function and 150 to this function. I'll just go ahead and tell you that C of 151 minus C of 150 is, and I'll just give you the punchlines here, 3448.19, so I've already rounded to 2 decimals, minus 3433.75, which is roughly 14.44. Because I have to say roughly because these are both rounded answers. And it says to compare it to the answer we got in part B. Look, this is the actual slope, right? The actual slope between these two values, because realize the x values were 1 apart. So when you do the y2 minus, this is y2 minus y1. But x2 minus x1 is 151 minus 150, so it's just 1. This is the slope between those two values, the actual slope between those two values. You can't produce 150 and a half items. That doesn't work. So you can only produce 150 or 151. This actual slope between them is 1444, so it actually costs a little bit more to produce that 151st item than our first derivative predicted. However, because they were so similar, what you get to say is that this is, they say it's a good predictor. Pointing at the wrong thing. This is a good predictor of making the 151st item, is all it is. And that's because the values were very close to each other. How close is close? I guess that's subjective. But I assigned one of them in the homework, and it's either going to be close or not. Okay, and if it's not close, then it's not a good predictor of what the cost would be to produce the next item.
Why is that possible?
Why is what possible?
That it wouldn't be close.
I don't know. Honestly, maybe it's a weird function. Maybe it's got radicals in it. I mean, in my mind, if it's a polynomial, the first derivative should be a good predictor.
Yeah.
Unless, what if you can only produce things in batches of like 5 or something? You see, now what you're finding is an average rate of change between 2 points, whereas the derivative's not. You know what I'm saying?
Yeah.
Maybe that would change it. I don't know what kind of items you would only be able to produce in batches, but you get what I'm saying? Yeah, so if it's a smooth polynomial and you're going by one item at a time, I really don't see why the first derivative would not work. I can't imagine the shape. But if it's not a smooth curve, if it's got weird radicals in it in places, or maybe logs or exponentials, they might do weird things.
Okay.
Honestly, I don't know.
Yeah.
This is the kind of math that industrial engineers do.
Like the one that we don't know, or like this?
They do stuff like this
Okay.
in real life. Like I said, I have a friend, had a friend, I don't know if we're still friends, but anyway, he works up in Georgia for Lockheed Martin. He's an industrial engineer, and he schedules projects basically to maximize man hours, like to maximize the amount of work that's done while minimizing costs of things at the same time, and then allocating the hours appropriately to make sure that they make deadlines. He just does a bunch of derivatives and stuff like that. Or probably the computer does it for him. But He understands what it's doing, you know.
Yeah.
Alrighty, and the only, in my opinion, interesting question in these notes. Let me create the scenario for you. You have a triangle, has one side length of 12 and one side length of 10, but you have an unknown included angle between them. The implication here is picture not drawn to scale. That angle could vary. And imagine I was holding a yardstick and a meter stick. I was holding the 12 centimeters and holding the 10 centimeters and pulling those sticks apart. Pulling these apart, as the angle gets bigger, line BC would be getting longer. And as the angle gets smaller, line BC would be getting smaller. We can actually figure out the rate of change of the area of this triangle based upon theta. So what that means is we would need an area function in terms of theta. Luckily, we have one via trigonometry, finding the area of a triangle with two sides and an included angle. Area, and I'll use A of theta. Yeah, I guess A of theta. That's a weird thing to say, but theta is a letter. So area in terms of theta is 1/2 AB sine C. You know, the letters are not in the right order. That doesn't matter. This is just a generic formula. So our area in terms of theta would be 1/2. The two sides we know, 10 and 12. And the angle we don't know, sine of theta. So that's 60 sine theta. So given any angles between 0 and 90, for that angle, we can plug it in right there and we can see what the area is. So it says, you know, find the rate of change of the area at the time when theta is 60. It's not saying what is the area when theta is 60. It wants to know how fast is the area changing as theta grows from 0 to 90. Along the way, we'll take a quick peekaboo at 60 and see what the rate of change was. That means we need to find the derivative of our area function. What we're doing right now is called a related rate. And in calculus, what they do with these related rate questions is they say, they like to make up questions like, you've got a cone that's full of water, and the water is draining out of the cone at a certain rate. It's filling a cylindrical glass, and they give you some dimensions. And then they'll say, what is the rate of change of the height of the water in the glass with respect to time and things like that? So you go, okay, the cone is draining at this rate. That means the volume of the cylinder is changing at that same rate, but that volume needs to be written in terms of its unknown height, so I can find its derivative and plug in height, or plug in all those knowns. It's a really neat thing called related rates. One of my most favorite things about calculus is related rates, only because it's so freaking dumb, and I didn't get it, and then one day it just clicked and worked, and then I loved it from there on out. Okay, so derivative, a prime in terms of theta. What's the derivative of sine? Cosine. So our derivative is 60 cosine of theta. And we just want to know, what is that rate of change when theta is 60 degrees? Oh, okay. What is a prime of 60 degrees? So 60 cosine 60 degrees. And I don't have my unit circle memorized, so I'm going to draw a 30, 60, 90 triangle in quadrant 1. And then I'm going to go, okay, 30, 60, 90 triangles. There's always a, and this is, of course, in terms of ratios, a 1 across from the 30, a root 3 across from the 60, and a 2 as a hypotenuse. This gives me 60, and cosine is x over r, or adjacent over Ta-da!
Why did you do in the beginning? How did you do? I don't know. Like the 1/2 AB sine C.
Mm-hmm.
That's like a property.
Yeah, it's in our reference sheet.
Okay.
We did it. Here's the problem. It's
not
part of the
like
trig
this
unit that you
level.
learned a long time ago.
Yeah.
Well, actually, you learned it twice from me, didn't you?
Yeah.
Yeah.
I remember the equation. I
Mm-hmm.
don't remember what it's used for.
It's used to find the area of a triangle when you have two known sides with an unknown included angle.
Okay.
Or if it's side angle side. It uses side angle side to find the area of a triangle
Okay.
instead of 1/2 AB sine C.
How did you know that that was side A and that
One
was?
half. And, oh no. A and B are just generic placeholders for the side links that you know.
Oh, okay.
It doesn't matter what side it was actually on. If you have side angle side, little a and little b are the two sides you know, and
Okay.
the angle is the one. It's called included. It's the one between them.
Got it.
Good. All right.